atomic void. If the nucleus of an atom were the size of a football, the nearest electron would orbit about a mile away. Everything in between is just gap. Not air, not filler, not anything. Pure emptiness held in geometry by forces you can't see. And this applies to everything you've ever touched. Your hand, this screen, the chair you're sitting in, all of it is almost entirely empty space. The reason it feels solid is because the electron clouds surrounding every atom repel each other electromagnetically. You're not actually touching anything. You're feeling the push of invisible fields keeping two clouds of emptiness from passing through each other. Matter isn't stuff packed tightly together. It's mostly gap, held in shape by forces. And the gap inside a single atom is already so extreme it breaks your intuition about what solid even means. This is the smallest void that exists, and it already doesn't behave the way you'd expect. Quantum vacuum. Now scale up slightly, not in distance but in concept. Forget matter entirely. Take a region of space and remove everything from it. Every atom, every particle, every photon. What's left? Not nothing. Not even close. Even in a perfect vacuum, space itself is doing something. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for tiny fractions of a second before annihilating each other and disappearing. This isn't theoretical hand-waving. The Casimir effect proves it. Take two metal plates and place them nanometers apart in a vacuum. They get pushed toward each other by quantum fluctuations in the space between them. You can measure it. You can repeat it. The force is real, and it comes from empty space. Zero-point energy means the ground state of space isn't stillness. It's a low-level hum that never stops. The universe's baseline, nothing, is already doing things, already exerting force, already refusing to be truly empty. Interplanetary void. Leave the quantum world and zoom out to a scale you can almost picture, the space between planets. It looks empty, and compared to a room full of air, it basically is. But the interplanetary medium is threaded with solar wind, magnetic fields, cosmic rays, and fine dust streaming outward from the sun in every direction. There's structure in there, just almost nothing to carry it. Earth to Mars at closest approach is about 33 million miles. The vast majority of that distance is essentially nothing, and that's just the gap between two neighboring planets. The solar system stretches out to roughly 100 astronomical units if you include the outer edges of the heliosphere. And the objects inside it, every planet, every moon, every asteroid, every comet, take up a fraction of that volume. The solar system isn't really a collection of objects. It's a collection of gaps with a few rocks scattered through them. Interstellar void. Zoom out further and you leave the sun's influence entirely. Now you're in the space between stars and the scale shifts in a way that's hard to absorb. Proxima Centauri is the nearest star to our sun at 4.2 light-years away. If you traveled there at the speed of a commercial jet, the trip would take roughly 4 million years, and Proxima is our closest neighbor. The interstellar medium fills this space with thin gas and dust, but the density is so low, it's a better vacuum than anything we can manufacture on Earth. The best vacuum chambers humans have ever built still contain more particles per cubic centimeter than the average interstellar medium. Stars are islands in an ocean with almost nothing in it. The light between them crosses distances that make the interplanetary gaps look trivial. The local bubble. Some of that interstellar space gets carved into something more defined. About 1,000 light-years across, centered roughly on our solar system, there's a cavity in the interstellar medium called the local bubble. It was hollowed out by a series of supernova explosions over the last few million years. Those blasts pushed the surrounding gas outward, leaving behind a region filled with hot, thin, X-ray emitting plasma. Not a true vacuum, but far less dense than the interstellar medium surrounding it. Almost no new stars form inside the local bubble. The gas is too hot and too spread out to collapse under gravity. Star formation needs dense, cold clouds, and the bubble doesn't have them. Recent research suggests the expanding shell of the local bubble may have actually triggered star formation in nearby regions, compressing gas at its edges into the stellar nurseries you can see today in places like Orion. We've been living inside this structure for millions of years and only mapped it in detail recently. Intergalactic void. Leave the local bubble and leave the galaxy entirely. Now you're in intergalactic space and the emptiness reaches a different level. The gap between the Milky Way and Andromeda is about 2.5 million light-years. Light, traveling at 186,000 miles per second, takes 2.5 million years to cross it. A handful of rogue stars and stray gas clouds drift through that space, but the density is almost immeasurably low. Unlike interstellar space, intergalactic space has almost no magnetic fields, almost no dust, almost no structure of any kind. It's as close to true nothing as the universe gets at this scale. And this gap between two neighboring galaxies is just the small-scale version of what comes next. Mini-voids. Zoom out to the cosmic web, the large-scale structure of the universe, and you start to see pattern. Galaxies cluster into filaments and walls. Between those filaments sit voids. The smallest of these are called mini-voids, localized underdense regions scattered through the web like potholes in a road. They're not completely empty. They just have roughly 1/10 the galaxy density of the surrounding regions, and they're hard to study precisely because there's almost nothing there to observe. You find them by noticing the absence, by mapping where galaxies aren't, and inferring the shape of the gap from what surrounds it. Mini-voids sit inside the larger filament structure, occupying the spaces between galaxy clusters and walls. They're small-scale previews of something much larger. The local void. On the edge of our own cosmic neighborhood sits a much bigger version. The local void stretches roughly 150 million light-years across and borders the region where the Milky Way lives. It's one of the reasons our galaxy is moving the way it is. The local void is underdense, which means its gravitational pull on surrounding matter is weaker than average. Galaxies near it don't get pulled in, they get pushed away, streaming outward toward denser regions. The Milky Way is one of them. The Cosmic Flow surveys, which tracked the motion of thousands of galaxies by measuring their velocities and distances, revealed this flow in detail. Matter is draining away from the local void in every direction toward the filaments and clusters that surround it. It's not sitting there passively. Its emptiness has consequences. It's actively shaping how our corner of the universe moves. KBC Void. Go bigger, much bigger. The KBC Void, named after astronomers Keenan, Barger, and Cowie, is roughly 2 billion light-years across. Our Milky Way sits near its center. We're not just near a void, we're deep inside one. The density inside the KBC Void is about 20% below the cosmic average. Not empty, but noticeably underdense over an enormous volume. And that underdensity may be doing something measurable. One of the biggest unsolved problems in cosmology right now is the Hubble tension. The fact that local measurements of how fast the universe is expanding don't match measurements based on the early universe. If we're sitting inside a large underdense region, local expansion rates would appear slightly higher than the cosmic average, which could explain part of that discrepancy without requiring any new physics. The KBC Void might be distorting our view of the universe from the inside. Cosmic voids. Pull back further, and the KBC Void is just one example of a whole category. Cosmic voids are the large-scale structural gaps between galaxy filaments and walls, the spaces that make up most of the universe's volume. A typical cosmic void runs 100 to 300 million light-years across. Galaxy density inside them sits around 20% below the cosmic average, though some are emptier than others. A few galaxies do exist inside voids, and they tend to be smaller, bluer, and more isolated than galaxies in filaments. They evolve differently when there's almost nothing around them. Voids dominate the universe by volume. The filaments and clusters are thin threads. The voids between them are the bulk of what's out there. And because their size, shape, and growth rate respond to dark energy, they're one of the better tools cosmologists have for testing how the universe behaves at the largest scales. Supervoids. Some voids grow so large they stop fitting the normal category. Supervoids are underdense regions hundreds of millions to over 1 billion light-years across, and they form through the same gravitational process as smaller voids, just pushed further than the standard model of cosmology is comfortable with. Finding supervoids as large as some of the observed ones, as early in cosmic history as they appear, is a genuine problem. They shouldn't have had time to grow this big given the age of the universe, and they leave a physical mark on the oldest light we can see. When photons from the cosmic microwave background pass through a supervoid, they lose a small amount of energy through a process called the integrated Sachs-Wolf effect. That energy loss shows up as a cold patch in the CMB, a region slightly colder than its surroundings. You can detect a supervoid by looking at light that passed through it billions of years ago. The Boötes Void. The most famous supervoid has its own name. The Boötes Void was discovered in 1981, sits in the direction of the constellation Boötes, and stretches roughly 330 million light-years across. Inside it, there are about 60 galaxies. Based on the density of surrounding regions, there should be thousands. The void is so empty that if you lived inside it, the nearest galaxy would be so far away that for most of human history, no telescope would have been powerful enough to see it. You'd have had no evidence that anything existed beyond your own galaxy. The universe would have looked like one island in an infinite dark. When it was first mapped, its size troubled cosmologists. Structures like this weren't supposed to exist. The leading explanation now is that the Boötes Void may actually be several smaller voids that merged over time, which makes more structural sense but still isn't fully resolved. Giant Void. The Boötes Void held the size record for a long time, then surveys of large-scale structure turned up something larger. A RLP-36, sometimes called the Giant Void, is a candidate supervoid estimated at over 1 billion light-years across. It's less studied than Boötes, and its true size is still being refined as survey methods improve. But if the estimates hold, it's one of the largest single underdense structures ever cataloged. Structures at this scale start to test a foundational assumption in cosmology called the cosmological principle, the idea that the universe looks roughly the same in every direction when you zoom out far enough. If voids 1 billion light-years across are real and not statistical artifacts, the universe may be less uniform at large scales than the standard model assumes. That's not a settled question. It's an open one. Eridanus supervoid. One of the most debated supervoids is tied to something visible in the oldest light in the universe. The cosmic microwave background, the faint glow left over from the early universe, has a cold patch in the direction of the constellation Eridanus. It's about 70 microkelvins colder than its surroundings and covers a region roughly 1 billion light-years across. That temperature difference was first detected by the WMAP satellite and is held up in subsequent observations. One explanation is a supervoid along the line of sight. Photons passing through an underdense region lose energy through the integrated Sachs-Wolf effect and arrive slightly colder. Galaxy surveys have found some evidence for an underdensity in that direction, but whether it's large enough to fully account for the cold patch is still contested. The supervoid explanation works in principle, but may not be sufficient on its own. The alternative is that the cold spot is a statistical fluke, an anomaly that looks meaningful but isn't. Some proposals go further, suggesting it could be evidence of a collision between our universe and a parallel one. That idea has no confirmed support, but the cold spot is real, and no explanation has fully closed the case. The eternal void. Zoom all the way out. Past the observable universe, physics suggests the same pattern continues. Voids, filaments, clusters, walls, repeating at scales we can't directly see, possibly forever. And in the far future, that pattern dissolves. Accelerating expansion pulls galaxy clusters apart. Filaments stretch and break. The cosmic web unravels slowly over trillions of years until the universe itself becomes one giant void, a space so expanded that nothing is close enough to anything else to interact. No stars forming, no light crossing between galaxies, no structure left to speak of. This is the heat death endpoint, not a bang or a collapse, just a slow thinning into permanent total emptiness.